Hello friends, so today we are going to solve 3 questions, and these 3 questions are from electrostatics. And so the first question, it states that suppose 3 positively charged particles are constrained to move on a fixed circular track. Suppose 2 charges and the fields of the charges are equal, and the equilibrium arrangement is such that these 2 charges are 90 degrees apart. What is the relative magnitude of the third charge? So in this case, you have to remember there are 3 charges and they are moving in a circular track, but it is a constrained motion. And so we can just, you can say, draw the approximate figure. And so this is a circular track, and let us suppose this is center, and we have 2 charges, and these 2 charges are 90 degrees apart. Okay. And suppose this is the position of first charge and this is the position of the second charge. Okay. Or other than that, okay, let me. So here we are going to use the formula for our tangential force on the charges. For that, let me draw specifically for that formula. And let us suppose this is our charge, second charge, that is charge B. Okay, and this is specifically for the formula part. And let us assume that this B is making an angle of theta j, and this A is making an angle of theta I. And in this case, we have to remember that there is a constrained motion. Okay, constrained motion means that the radial part of the, or we can say radial component of the force, will be balanced by the automatically according to the centripetal force. Okay, so we are only interested in our tangential force. Okay, that's the meaning of constraint. Okay, there is some kind of, you can say it is tied with the string, something like that. Because of that, it is going to rotate in this fixed circular track. So we are only interested in the tangential motion. We are not interested in the radial motion, or you can say the radial force. And so we can write that we consider 2 charges, and these 2 charges are, let us suppose, Q of I and Q of j. Okay. And they are placed on a circle whose radius is our R. And at the angular position, and let us suppose for Qi we are having theta I, and for Qj we are having theta j. Therefore, we can write the formula for the tangential force. Therefore, we can say that tangential force on charge I due to charge J. And this formula will be giving us Fij, and this is a tangential force, will be equal to K Qi Qj r square divided by multiply by sine of theta I minus theta j and divided by 2 minus 2 cos of theta I theta j and whole raised to power 3 by 2. Okay, so this is the formula for our tangential force. Okay. And we can also drive this formula. It's not much difficult. Okay, so let's drive this. So that is going to help to understand certain things about this force also. And for that, okay, so we can say the position vector of the charges on the circle position vector on the circle, and this we have placed in xy plane. Therefore we can write that for our first charge, that is I charge, we are going to get this as our cos of theta I and sine of theta I. Similarly, we can write for our position vector for the j charge, and that will be equal to our cos of theta j and sine of theta j. And so you can just draw an approximate. So this was our center C, and this was charge A and placed in a circle. So this was our charge B, and the position vector was, this was our Ri, and this was our Rj. Therefore we can find out the separation vector from J to I. Therefore we can write that Rij will be equal to Ri minus Rj, and we are only interested in the magnitude. So we can say that our Rij magnitude will be equal to r square, and we substitute the value also, so we can easily square it, and this we get as cos of theta I minus cos of theta j whole square plus sine of theta I minus sine of theta j, and this is a whole square. And if we expand and solve it, okay, so we are going to get this as a cos square, and there will be sine square, and cos square theta I will be there, sine square theta I will be there. Similarly, we are going to have cos square theta j and sine square theta j. Okay, so that will be 1 and 1. So we get this as a r square, and we get this as 2 minus 2 cos of theta I minus theta j. And therefore we can say that the magnitude will be equal to, because this is our Rij whole square, so this will be coming as r, and this will be 2 minus 2 cos of theta I minus theta j, and its square root. So we got the value of the distance between the two charges basically. Now we can easily use the Coulomb's law. Okay. So we can say that Coulomb's law and that gives us the force between the two charges equal to K times Qi Qj, and we have this as Rij vector and divided by the Rij and its magnitude whole cube. Now we simply substitute them. So we get this as our K Qi Qj divided by R square, and in the numerator we are going to get this as cos of theta I minus cos of theta j, comma, this will be our sine of theta I minus sine of theta j, and denominator we already know the distance, the magnitude, and that comes as 2 minus 2 cos of theta I minus theta j, and this will be coming as 3 by 2. Okay. And like I said, we are only interested in the tangential part because the radial part is going to take because of the constraint motion. Okay, constraint motion we can think it like that the charges are rotating in the circle, and suppose they are being held by a light string, okay, some sort of force that is holding them. Okay, so the radial part of the force or acceleration, everything will be taken care by that constraint motion. So we are only interested in the tangential part. Therefore we can say that the tangential unit vector okay, and let us call this as our Ti unit vector, and that will be equal to our minus, this will be sine of theta I and cos of theta I. Okay. And this we can project in the force to find out its tangential part. Therefore we can write from here, project force onto the tangent. Therefore simply we can say that because of this we are going to get the tangential part or tangential component, and let us call this as Fij, and tangential will be equal to our force and the unit vector. Okay. Now we can easily find out this dot product. Okay. And so we are only going to solve the right side, so we can say this will be our cos of theta I minus cos of theta j, and this is minus sine of theta I plus sine of theta I minus sine of theta j multiplied by cos of theta I. And this we can expand it further, and this will be giving us minus cos of theta I sine of theta I plus cos of theta j sine of theta I, and that will be plus, this is our sine of theta I and cos of theta I minus sine of theta j and cos of theta I. And so these two terms are going to cancel out. Therefore, we will be left with only our cos of theta j sine of theta I minus sine of theta j and cos of theta I. And this is nothing but our sine A cos B minus cos A sine B, which is sine A minus B. Therefore, we get this as our sine of theta I minus theta j. Okay. And we can easily put into the tangential part. Okay. Therefore, we get that our tangential force is the formula which we have written in the starting. Therefore, we can write that the tangential force will be equal to k qi qj upon r square and sine of theta I theta j, and this comes as about 2 minus 2, and we have our cos of theta I minus theta j and whole 3 by 2. Okay, so this is our basic formula. Okay, and this is not the actual solution. Okay, because we just derived where it went. Yeah, so we just found out this particular formula. Okay, so this is the entire derivation of the formula. That's the value of the tangential force. Okay. Now we come to our main question, and so we are given two charges, and these two charges are basically there are three charges. Okay. So this is our suppose center C, and we are given two charges, and let us suppose this is a charge at A and we are having a charge at B. Okay. And let us call this as our theta 1 and this is our theta 2. And so this we call as a plus alpha, and this will be obviously our minus of alpha. Okay. And they are all placed in the circle. Okay. And this circle is having a radius of r. And we assume that we are having a third charge, and third charge suppose is our capital Q, and it is also given in the question that charges at A and B are having the same magnetic field also, electric field also. So obviously their magnitude will be same, that it will be Q as well as charge will be at B will be also Q. And this capital Q charge, that is third charge, it is at an angle of theta. And we are supposed to find out this value of theta first. Okay, then we can say further solve it. An important part is that everything is in equilibrium. Okay, so basically in the question it is given that all the electric field at A and B are in balance with each other. Okay, this statement is important here. So we are given that two charges, field of the charges are equal and in equilibrium. Okay, but the angle between them is given as 90 degree. Okay, so we have to find out this value of theta, and you can solve this by using two methods. Okay, let's use the more traditional one. Okay. And we assumed that we have considering two charges. One charge is placed at A and it is having a Q and its angle is theta 1, which is our plus alpha. Second charge is at B, Q and that is our theta 2, and it is our minus alpha, and the angle between them is 90 degree. Okay, therefore we can say that this 2 alpha will be equal to 90, and this gives us that alpha will be equal to 45, okay, which is nothing but our theta 1 as well as theta 2, and we have this is our known angle which we are going to find out. And in the question it is mentioned that we are having condition for equilibrium on the circle. Condition for equilibrium on a circle, and it is given that the charges are constrained to the circle. Therefore we can say that the equilibrium means that tangential force on each charge is equal to 0. Tangential force on each charge is equal to 0, because radial force will be taken care by the constraint mode. Okay, so we are only interested in tangential part, and tangential formula we have already found out. Okay, and so let us solve it for our tangential force. So we can say tangential force on the charge at A, that is plus alpha. Tangential force on charge at A, which is at our plus alpha. So obviously there will be two contribution, and so first will be because of our charge at B, and which is at a minus alpha. Okay, so this will be your first contributor, and for that we can write the formula that the force between these two charges as tangential force will be equal to k q square, and this is r square, and we get this as sine of 2 alpha and 2 minus 2 cos of 2 alpha, and this is our 3/2, and we know that our alpha is 45. Therefore sine 90 will be equal to 1, and therefore we can say that sine of 2 alpha will equal to 1, and 2 minus cos of 2 alpha will be equal to 2, because our this cos 90 will be equal to 0, and therefore we can write that the tangential force between the two charges q and q, that is A and B, will be equal to k q square, that is 2 square root of 2 and our r square. Now we have a third charge, that is our q. So we can say from charge q, and yeah, so now we are going to deal with this charge q. Therefore we can once again write the formula for tangential force. So we can the force between this q and capital Q in tangential direction will equal to k q r square, and this comes as a sine of alpha minus theta and 2 minus 2 cos of alpha minus theta and whole raised to power 3/2. And under equilibrium, these two tangential forces should be balancing each other. You can say at equilibrium, that the tangential force FQQ tangential plus FQ capital Q tangential should be equal to 0. Now we simply substitute their respective parts. So we get this as K Q square upon 2 R square plus K Q capital Q and R square, and this comes as our sine of alpha minus theta 2 minus 2 cos of alpha minus theta, and we have this as 3 by 2 is equal to 0. And we can just remove this k, this q square, and r square we can just move it. So we will be left with q upon 2 square root of 2 plus q, and this is our sine of alpha minus theta 2 minus 2 cos of alpha minus theta, and this is whole raised to power 3 by 2 is equal to 0. Now similarly we are going to solve for charge at minus alpha. So you can say that our similarly charge at B, which is our minus alpha. By same process we are going to same, but only the minus sign will be there. So this will be minus q 2 root 2 plus q, and this comes as a sine of minus alpha minus theta 2 minus 2 cos of minus alpha minus theta, and this is over 3 by 2 is equal to 0. And we are going to solve these two equations. Let us see equation number 1 and equation number 2. So simply we are going to subtract these two equations. Okay. So we can say our 1 minus 2. So we get this as our, this will be minus minus plus. So we are going to get this as our q upon square root of 2 plus q, and we have this as sine of alpha minus theta divided by 2 minus 2 cos of alpha minus theta, and this is whole 3 by 2 minus, and this sine of minus alpha minus theta divided by 2 minus cos minus alpha minus theta whole raised to power 3 by 2 is equal to 0. And we know that sine minus x is minus sine x and cos minus x is cos of x. Okay. Therefore we can write this as our q upon square root of 2 plus q. We get this as sine of alpha minus theta, and this will be minus sine of alpha plus theta divided by, and let us take this as a d1 denominator whole raised to power 3 by 2, and this as our d2 denominator whole raised to 3 by 2 is equal to 0. And this d1 and d2 is equal to 2 minus 2 cos of alpha minus plus theta. And we want that these terms should be balancing, cancelling each other, or they should be a constant independent sign. And for that we can write that, you can say that for two sine terms to combine, d1 should be equal to d2, or in terms of equation, we can write this as our cos of alpha minus theta should be equal to cos of alpha plus theta. And we can use the identity, this cos A minus cos B. Okay. And so from this we can write that our sine of alpha minus sine of theta is equal to 0. But we are given that alpha is 45 degree. Therefore, we can write that our sine of theta is equal to 0, or we can say that theta is equal to over pi. So we found out that the angle of the third charge should be lying at angle of 180 degree, okay, or we can say pi, and this is for equilibrium. And now we come to our this. Okay, so we found out the location of all the three charges. Okay. So this is was center C. So charge is at A. Then we are having charge at B. And this is angle 45. This is angle 45. And with respect to here, we are going to have an angle of 180 degree, and this is the position of charge Q. So we found out that position of our charge Q, or we can say the angles with respect to all the things. Okay. And now we can easily find out the chord length between all these charges. So we can say that chord lengths, and the chord length between the charge, this is a charge Q and this is also charge Q. So we can say this as dQq will be equal to 2r, and the angle is our 90 degrees, so this will be coming as sine of 45. So this will be square root of 2 times r. And then we can find out our chord length between this capital Q and small q, that will be equal to over 2r, and sine of, so this angle will be our 135. So we get sine of 135 divided by 2, so that will be close to 67. So we can say this is equal to our 67.5. Therefore we get this as r square root of 2 plus square root of 2. And the forces on the equal charge, okay, so we can just pull out the forces now. So you can say the forces FQQ will equal to K Q square, and this is square root of 2 R whole square. So we can say this comes as K Q square upon 2R square. And similarly for our F capital Q and small q will be equal to K QQ upon R square root of 2 plus square root of 2, and this is a whole square, which gives us K product of two charges, and this will be a 2 plus square root of 2, and this comes as our R square. And so next we can come to our tangential component, because we are only interested in the tangential parts. Okay. And for that we can just draw approximate figure. Okay. So this is a circle, and we have center C. We are having charge at A, other charge it as B, and there is a third charge at Q. So let us consider that we are going to find out all the forces for this A. So we are going to consider everything with respect to A. So we have charge, same charge, here it is also Q and here it is also Q. So obviously there will be of course a repulsion, and we can just draw it. So it will be in this direction. And let us call this as FQQ, and this angle is about 45, so this is about 90, so this will be also 45, and we can easily divide it to two components, and this will be our other component. So this will be 45. So we are, like I said, we are only interested in the tangential part, so this will be FQQ sine of 45. And then we come to our this here, it will be also tangential in this direction. Okay, so let me move this. So it will be something like this. We can also divide it into two components now, and one will be the tangential component. So this is F Q capital Q. So this will be F capital Q, and so let me, and this we know is our 135. Okay, and so this angle will be close to 22.5. So this will be also 22.5. So we get this as our FQQ sine of 22.5, and this will be FQQ cos of 22.5. And we are only interested in the tangential part. So we have two forces tangentially, this as well as this. And for equilibrium, these two forces should be balancing each other, because in the constrained motion, this, you can say our radial force will be automatically balanced because of the constrained motion. Therefore, we can write that the tangential components and the tangential component, first one is our F small qq tangential, and that is our F qq, and we have this as sine of 45, and we have second tangential component, that is between our, this is equal to F q capital Q, and this is sine of 22.5, and at equilibrium these two must be equal. So you can say at equilibrium our tangential force because of small q charges should be equal to tangential force between small q and capital Q. So we get this as our FQQ sine of 45 is equal to F small q capital Q sine of 22.5, and we substitute the values, and we get this as our FQQ we know already is K Q square upon 2R square, sine of 45 is 1 upon square root 2, and this is equal to our K Q capital Q, and this is about 2 square root of 2 and our R square, and we have this as sine of 22.5 is our square root of 2 minus 2 divided by 2, and we can just cancel out this R square, this square goes away, K goes away, and this 2 goes away, Okay, therefore we get that ratio of these two charges will be 1 plus square root of 2. So it means our capital Q will be equal to 1 upon square root of Q, and approximately this is 2.414 times Q. Okay, so this is the value of the charge on this capital Q, so that all the three charges are in a constrained motion and in equilibrium. Please remember, it is constrained motion, so the radial forces will be balanced according to the constrained motion. Okay, that we can say, like if you trade something by using a string, so radial force will be automatically balanced by our tension, and that is required. So we are only interested in this case the tangential force. So this is important part here. Next question. It is given that a thin plastic rod bent into semicircle of radius r has a charge q distributed uniformly over its length. Find the electric field at the center of the semicircle. This question is comparatively quite easy. And so we are given that we have a semicircle or wire rod that is bent in the form of a semicircle. So bent in the semicircle, and let us suppose this is center C, and its radius we have assumed is our r. Okay. So we can say that we have a rod, and rod length is suppose given as capital L, and this rod is made into a semicircle. Therefore we can say that our L is equal to pi times r, and we can say that the total charge, let us suppose, on this entire semicircle is capital Q. Total charge is our Q. Therefore we can easily find out the linear charge density. Linear charge density, let us say lambda. Lambda will be equal to our total charge divided by the pi r, that is our length. And so in this case, let us assume that we consider a small element, and that small element is having a charge dq, and this angle is given as our d theta, okay, and they are at angle of theta. Okay. So we considered an element of charge dq at angle theta. Therefore we can say that our charge on this element dq will be equal to charge density and r d theta, and theta we know is going to from 0 to pi because it is only half. Therefore we can say that our electric field at the distance r, when it's electric field at r, we can write this as our dE will be equal to k dq upon r square. We can substitute our dq, and this comes as our k lambda r d theta upon r square. This cancel out, therefore we get our electric field because of this small element is our k lambda upon r times d theta, and the direction will be radially inward toward the center. It will give our radially inward toward center. And because of this, if we resolve this into two components, so we can say that the horizontal component are going to cancel each other, horizontal component cancel, and you can say that only vertical component survives. Only vertical component remains. Therefore, we can write that the vertical component that is our dEy will be equal to dE sine of theta. Okay, so like I said, it is radially inward toward the center, so it will be something like this, and this angle is of theta. So we are going to have here, this is our dE, so this will be dE cos of theta, and this will be our dE sine of theta. And correspondingly there will be another opposite end symmetric to it, which is also going to have something like this, and its component will be our, this horizontal component will be balanced by the horizontal of it, and only surviving part will be our vertical component. Okay. Therefore, we can say that our dEy, we substitute value of dE, that is k lambda upon r, and we have this as sine of theta and d theta. So total electric field E of y will be the integral of our, this is our vertical component, and so we get this as our E of y will go to k lambda upon r, we can take as common, so this comes as our sine of theta d theta, and theta varies from 0 to pi. And the integral is our 2, so we get that our vertical component or total electric field, this will be 2k lambda upon r, and we substitute value of lambda, so we get our E of y will be equal to 2k q upon pi r square. Okay, because we know our lambda is equal to q upon pi r. So this is our electric field at the, for the semicircle. Now we come to the third question. And this third question, it states that a charge q is distributed uniformly around a thin ring of radius b that lies in the xy plane with its center at the origin. Locate the point on the positive z-axis where the electric field is strongest. Strongest basically means maximum. And this is comparatively easy, because here we are indirectly solving for the electric field of a ring along its axis. So suppose this is our ring and this is the axis. So radius is given to us as b, and we have said that we have to solve it for positive z-axis. So let us suppose this is our z, and therefore we can write that electric field at on the z-axis, we can say that our field on z-axis, we can say that is our E of z will be equal to 1 upon 4 pi epsilon naught, and this comes as q z and z square b square, and we have 3 by 2, okay, which is the standard formula. And we have to remember that we are going to solve it for positive z-axis. Okay. and we want that this electric field should be strongest, mean maximize. And for that we are going to find out value of Z. So we can say that we maximize E of Z for Z greater than 0. So we are only interested in this part. Let us denote that as f of Z is equal to Z upon Z square plus B square, and this is our 3 by 2. So obviously we are going to derivate it and equate equal to 0. Therefore we can say df upon dz. This will be giving us Z square plus B square and minus 3 by 2, and this will be minus 3 Z square, and this comes as Z square plus B square and 3 by 2. And we can just make a minor adjustment. So we get this as our df upon dz will be equal to, and this is minus, so we take it as a positive. So this comes as Z square plus B square, and we have this as our 5 by 2, and Z square plus B square minus 3 Z square, and this will be equal to our B square minus 2 Z square, and it comes as our Z square plus B square, and we have this as 5 by 2. So obviously for maximization equal to 0. Therefore we can say that B square minus 2 Z square is equal to 0, which gives us that our Z square is equal to B square by 2. And in the question it is given that we have to solve it for Z only the positive. So Z is greater than 0, because here we are going to get Z is equal to plus minus B upon square root of 2, but we need only positive values. Therefore we get that Z is equal to B upon square root of 2. If required, we can just you can say verify its maximization also. So we check for Z less than B square root of 2, we get that the derivative is greater than 0, and for Z with greater than B square root of 2, we get that our derivative is less than 0. So means that our this point is a maxima. So that was our required. We have to find out value of Z so that the field, electric field is strongest. Strongest means maximum. Okay. So this question was comparatively easy, but only trick they have said, because we have multiple times we have used this particular relationship, and they only ask to find out the maximization of the point of the electric field. Okay, and for that we found out what will be our value of Z. Okay. So except the question number 1, which was a little bit tricky, and in that case we have to remember one important term that is mentioned in the question, that is our constrained motion. And because of the constrained motion, if the body is their charges were revolving in the circle, the radial part will be balanced by the constrained motion. So we have to keep focus only on the tangential force or tangential part. Okay, forces in case the charges, otherwise if there are no charges, then we have to take care of the tangential part. Okay, so, and the second was also comparatively easy. For semicircle, we found out what will be the value of electric field. But let me mention it here once again, that for our question number 1, the important term was our constraint. Okay, and in this case, in this particular question, we were given the 3 charges and they were constrained to move in a circle. So whenever we say that a constraint to move in circle, so for any random positions, the radial part of everything, whether mostly it will be forces because these are the charges, like charges, so obviously they are going to repel each other. Okay, something like this. And here also. So we can divide these forces into 2 components. One will be a radial part and other one will be a tangential part according to their location. So this radial part will be balanced by the constrained motion. Okay, so constrained, we can assume that suppose these charges are tied with the string, okay, so that they do not run away. So the constrained motion is with respect to the string. So this radial part will be balanced by this constrained motion. So we are only interested in this tangential part. We should be at equilibrium, so they should be equal. Okay, so we have to take care of this only one term, that is our constrained motion. So this completes all the 3 questions. Thank you.